All right, let's go ahead and get started. So we're going to backtrack just a little bit to section 3.8 because people had some questions about both relative and absolute error, as well as some of the Taylor polynomial stuff. So I thought we'd go back a little bit and talk about that for a minute. So let's talk about relative and absolute error. And yeah, some common examples of relative and absolute error are measuring the volume of a sphere. That's kind of a typical example. Let's talk about kind of how that works because I imagine it's going to come up frequently or semi-frequently. So let's say we have the following situation. Sure, I like this. The diameter of a sphere is measured to be, what have I got here? 30 centimeters. If the diameter increases by 2 centimeters, what is the here? Yeah, what is the relative? That's not quite the word I want to use here. Let me see. Let me make sure I phrase this the right way. Yeah, I don't love the wording here. Yeah, I guess what is the relative change and the absolute change in volume? So there's a couple ways to think about doing this. Really, it all comes down to using linearization to approximate the change and then kind of seeing what that is. So let's write what we know. We have that the diameter is 30 centimeters. So we really care more about the radius. The radius of our sphere is 15 centimeters. And the radius, since the diameter is increasing by 2 centimeters, the radius is increasing by 1 centimeter. So we're essentially going from a radius of 15 to a radius of 16 centimeters. The numbers are going to be not pretty, such as life. Sometimes the numbers aren't pretty. So let's find the volume here and the volume here, even though it's going to be kind of, we're going to do it exact first, just kind of see what the actual numbers are. And then we'll talk about how we would really do the estimating of the change. So the volume here is going to be 4/3 pi times 15 cubed. And I guess I'll need a calculator. So let's see here. 15 to the third power divided by 3 times 4. We're getting 4,500 pi cubic centimeters. Pretty nice. How lovely. Over here, same deal. 16 to the third times 4/3. Oops. Come on, James. 16 to the third, you know that. Times 4/3 times pi. So here we're getting something not quite as nice. We're getting approximately, we're getting 4/3 times pi times 16 cubed, which is approximately 5,461.3 pi cubic centimeters. So the actual difference here, the change in volume, is going to be that amount minus that amount, which is going to be 961.3 pi. And just as a raw number, that doesn't really tell us a lot, right? Great, the volume increased by about 2,700, almost 3,000 cubic centimeters. But if you don't know kind of the original amounts, it's not a very meaningful number. It's kind of like how a couple of weeks ago we were talking about populations growing, and we talked about how the relative growth rate was the thing that was actually meaningful, because if your population is growing at some number of people per year, that doesn't mean a lot if you don't know how many people there were to start with in your population. Same kind of idea here. So that's how we get the actual volume change. But again, that's not really the thing we like to do. So what we're going to actually do here is we're going to say the approximate change in volume. We typically call that, I don't know if he's used this notation, we typically call that the differential dV. So we're going to use dV to estimate delta V. So here's what I should really be saying. We've done this already. You just don't, the words I'm saying don't necessarily show that. Let's kind of bring it back to the linearization for a second. So in terms of the linearization, our linearization usually looks like this formula. L of x is equal to f of a plus f prime of a times x minus a. Where here's kind of the value you're estimating, here's the old y value, and here's how much it's changing by. This part right here, that's your differential dV, or I actually really say df because I'm using f here. That's your approximate rise. That's it. Or I should say that is your rise. That's approximating how much the function's actually changed. So what we're going to do here when we calculate dV, our dV is just going to be your derivative times how much you've increased kind of the input variable. So in this case, it's going to be your V prime times your delta R. Now this one actually kind of works out really nicely because when you take the derivative here, the derivative of 4/3 pi r cubed is 4 pi r squared, which is exactly the surface area of a sphere. So if you're trying to do it, you're saying, okay, we're making the sphere bigger and we're exactly adding as much volume as the entire surface area of the sphere times how much thicker you're making it. It works really nicely for spheres. That's why we use spheres a lot for this example, because they're kind of an easy way to visualize what's happening. It's kind of like you're painting a real thick layer of paint on this sphere and making it that much thicker, and how the volume of paint is what we're trying to estimate here. So we're going to say, great, the volume is going to be approximately this amount here, which is going to be the derivative of 4/3 pi r cubed. Right? Our volume is 4/3 pi r cubed. Our derivative is 4 pi r squared, and then we're going to multiply by how much r is increasing by. Back to the numbers we actually had, we were starting off with a radius of 15 centimeters. And then we're going to multiply that by how much the radius increased by, which is 1 centimeter. I don't need the units yet. And 4 pi times 15 squared is 4 times 225, which is 900 pi cubic centimeters. So this is our estimate of how much the volume changed. Which, again, if you look back at what we calculated earlier on, not too shabby. 900 pi versus 961 pi, it's a decent estimate of how much the volume increased by. So this would be our estimate of the absolute change in volume. And that, again, was 900 pi cubic centimeters. Question? So because of how our linearization formula works, so when we're talking about doing this thing here, we're taking kind of, so here's kind of, let me back up a little bit and kind of say, so what we're saying here is our linearization, which I'm going to use r instead of x, is going to be our volume at our nice value, 15, plus essentially what is the change in volume, which is going to be the derivative, right, the slope, multiplied by the run, which in this case is going to be our r minus 15. Yeah, that's right, yeah. And then we're trying to estimate the volume when the radius is now 16 centimeters. So we're going to plug in 16 for the R right there and say, oh yeah, so our volume at 16 is approximately L of 16. That should be a, yeah, which is going to be our old volume plus this derivative at 15 times 1. So now, here's what we've got. We've got our new volume estimate. We've got our old volume at 15. And then over here, what we're actually focused on is the difference between them. So if we're just focusing on the difference, we're just taking the derivative multiplied by the change in the input variable. You're welcome. And then the other thing we care about is the relative change. So the relative change actually is the actual change divided by the initial amount you started with. So in this, but we're not going to write that because we really don't want to do the gnarly looking numbers. We want to use the nicer numbers. So the relative change is approximately going to be our estimate of the absolute change divided by the initial volume that we started with. So in this case, that's going to be our 900 pi, which was an estimate of the change, divided by the initial volume, which if you go back to our beginning here, the volume when the radius was 15 centimeters was 4,500 pi. And so if we do the division here, that looks like it's going to be about 1/5, which seems surprising that that is the number we're getting. Let me think about that for a second. No, that's it. That makes perfect sense, actually. Yeah. So how do I say this the right way? 1/5 does seem. What am I missing here? 15. So usually when you go down by a dimension, you're getting a multiple of 3 typically. Sorry, I'm seeing a number that seems atypical to me. And I'm kind of trying to make sense. There's a very kind of common thing that happens here. Yeah, what am I missing here? Oh, I know what it is. All right, cool. Yeah. The radius increased by 1/15, right? It went from 15 to 16. And the volume increased by 3/15, 3 times the amount of radius. So usually I don't love this relative change here. That doesn't make a whole lot of sense in my mind, although it is a useful thing. What I actually kind of think is more useful to think about is the percentage increase. So I would point out that sorry, papers, that the radius going from 15 centimeters to 16 centimeters increased by 1/15. They don't really want to write as a decimal because it's just not lovely. And the volume going from a lovely 4,500 centimeters cubed to 5,400 centimeters cubed increased by 1/5. Since we're here, we might as well do the fun thing. Let's change it up a little bit. Let's say we're given the same sort of problem, except now we're going to be told that the radius increased by 4%. Same situation, right? Still measuring a sphere, or another way of phrasing this would be the error in measurement was 4%. I kind of like that better. I'm gonna change my phrasing here. Sorry, I know it's so. We measured the radius of a sphere accurately to within 4% of the actual value. Now the question is, how accurate is our estimate or our measurement of the volume? Okay, so here's what we know. We know that the radius is accurately within 4% of the actual radius. So what that means is, for our radius being accurate to within 4% means that however much we're off the radius by, so our delta R divided by the actual value of the radius is at most going to be 4%, or as a decimal, at most going to be 0.04. So if the radius was actually 100 centimeters, our measurement is within within 4 centimeters either way. So it's either as much as 104 or as little as 96. The delta R is at most 4, and the delta R divided by the R is at most 4 divided by 100, which is 0.04. Let me write that down. So now these are actual numbers, but for example, if the radius was actually 100 centimeters, that means our measurement is as low as 96 to as high as 104, which means our delta R, the amount our R is off the actual measurement by, is between +4 and -4. And then 4 divided by 100 is 0.04. So really what I should actually say over here, although it's kind of annoying, is that the absolute value of delta R divided by R is at most 0.04. Okay, here's what I think is kind of the fun part. So we're asked to find how accurate is the measurement of the volume, meaning what's the biggest percentage we could be off by the volume. Now, based on the work we just did in the previous problem, my guess is that it's going to be 12%, because essentially, however many dimensions, whatever you're like, the radius is a measurement that's in 1 dimension. The volume is the measurement that's in 3 dimensions. We're essentially going to triple our 1-dimension error into 3 times as much. If you were going for surface area, it would double it. If you're going from surface area to volume, I'm pretty sure you end up multiplying by 3 halves. It's kind of however much you're multiplying your dimensions by, that ends up happening, which I think is just kind of neat. Like, it seems like it wouldn't be always that, but it totally is. Cool. Anyway, here's what we're going to do. We're going to try to find delta V divided by V. Let's write out the formulas. So delta V, we talked about before how the change in volume we're going to approximate with this differential dV. And now we're going to say, well, our dV was the derivative V prime of R times delta R, and our volume is just the volume with the given radius. So now we're going to actually write in the formulas. The derivative of the volume is 4 pi R squared times delta R. And the volume is 4/3 pi R cubed. I always thought it was super cool how this always worked out when I was a student. So check it out. You can cancel 2 R's on the top and the bottom. You can cancel a pi. You can cancel a 4. And you're left with delta R over 3, or more nicely written, 3 times delta R over R. But look, we know that delta R over R is less than or equal to 0.04. So this is going to be less than or equal to 3 times 0.04, which is exactly 0.12, or 12%. So if the measure of our radius is off by at most 4%, the measure of our volume is going to be off by at most 12%. Kind of neat. And then to be perfectly accurate, we should put absolute values around every step of this, which is annoying. I shouldn't need it there, sorry. So that's a little bit about relative error versus absolute error. The absolute error is just the error in the measurement, whereas the relative error is the amount of error divided by the actual value to start with. And then if you want it as a percentage, you just multiply that by 100. So I would say that the relative error here is 0.12, and then the percentage error is 12%. Okay. Let's say a little bit more about Taylor polynomials as well, because it can be kind of, I feel like it's a very kind of, it's a big idea that's getting talked about for like this much of a minute, and then you're moving on. But here's all you really need to know about a Taylor polynomial. So someone might ask us to say, find the whateverth degree. Usually 6 is probably about as big as it's gonna get. Let's find the 6th degree Taylor polynomial. Of f of x equal to 1 over x centered at a equal to 3. Okay. So here's the very general formula. Your Taylor polynomial of degree 6, so p6 of x. We're just gonna write out the formula. We might skip a few things as we get far enough, but the formula starts off like this. It's going to be f of a plus f prime of a times x minus a, or the first two parts are just the linearization, right? It should look familiar. It's just the linearization. And then every subsequent piece, you're just making everything one more. And you're also dividing by something, right? So the next piece is not the first derivative, it's the second derivative times x minus a squared divided by 2 factorial. And the next piece is going to be the third derivative times x minus a cubed divided by 3 factorial. And so on until you get to the very last piece, which is going to be the sixth derivative times x minus a to the sixth over 6 factorial. So then after that, your job is to find all the derivatives, plug in the point, and then write it all out, which is super annoying, but it's not terrible. So let's find our derivatives. This is definitely where, instead of writing f of x equals 1 over x, I'm going to write f of x equals x to the negative first. So then my derivatives are not too terrible to take. My first derivative is going to be negative x to the negative second. My second derivative is going to be positive 2 times x to the negative third. My third derivative is going to be negative 6 times x to the negative fourth. My fourth derivative is going to be positive 24 times x to the negative fifth. My fifth derivative is going to be negative 120 times x to the negative sixth. And finally, my sixth derivative is going to be positive 720 times x to the negative seventh. So then we're going to take each of those and we're going to plug in 3, and then we're going to write out the whole entire formula. We might not write the whole thing out. It seems terrible. But let's start here. So f of 3 is just going to be 3 to the negative 1. You can write it as 3 to the negative 1. You don't have to rewrite it as 1/3, although you certainly could. And then f prime of a is going to be negative 3 to the negative second times x minus 3. I might write parentheses around that. And then the next part's going to be f double prime of a, so that's going to be 2 times 3 to the negative third divided by 2 factorial times x minus 3 squared. And it's not pretty, but it gets the job done. So then we have the next term, which is going to be f triple prime of 3, which is going to be negative 6 times 3 to the negative fourth. And then we're going to divide by 3 factorial times x minus 3 to the third. And then the next one, we're going to plug in 3 and get 24 times 3 to the negative fifth divided by 4 factorial times x minus 3 to the fourth. And then 2 more to go. We might as well finish it off. We get negative 120 times 3 to the negative 6 divided by 5 factorial all times x minus 3 to the 5th. And finally, the last term, 720 times 3 to the negative 7th, all over 6 factorial times x minus 3 to the 6th. Now, I will point out, because I feel like I have to, we could have simplified this really easily by noticing that that's 2 factorial and that's 2 factorial. 6 is 3 factorial. 24 is 4 factorial. 120 is 5 factorial. 720 is 6 factorial. So we really could have written this as 1/3 minus 1 over 3 squared times x minus 3 plus 1 over 3 cubed times x minus 3 squared minus 1 over 3 to the 4th times x minus 3 cubed plus 1 over 3 to the 5th times x minus 3 to the 4th minus 1 over 3 to the 6th times x minus 3 to the 5th, and finally plus 1 over 3 to the 7th times x minus 3 to the 6th. That's not necessary, but sometimes it's just easy to see that things are going to cancel nicely, and it makes sense to do it. So I picked kind of less than nice numbers on purpose just to show you that it can be kind of gross, but usually it's going to be better than this. For example, you all should write out the 4th degree Taylor polynomial of f of x equal to, I'll make it super nice, e to the x centered at a equal to 0. So go ahead and do that. So the nice thing about this example is that all of your derivatives are just e to the x, right? You don't even really need to write them down. We could, right? F of x is e to the x. F prime of x is e to the x. Yeah, we get the picture. They're all e to the x. So then we also picked a nice center as well. If our center is 0, that means f of 0 is e to the 0, which is 1. F prime of 0 is e to the 0, which is 1. So every f of a, or f prime of a, or f double prime of a, or triple prime of a, or quadruple prime of a is going to be just 1. So here we're going to get that our 4th degree Taylor polynomial is going to be 1 plus 1 times x minus 0 plus 1 over 2 factorial times x minus 0 squared, or just x squared over 2 factorial, plus 1 continues, like if you wanted to find the whateverth degree for Taylor polynomial for e to the x centered at a equals 0, it would just be that many powers of x divided by the corresponding power factorial. It's kind of the nicest Taylor polynomial we have. So there's our fourth degree Taylor polynomial. And then if they asked us to, let's say we wanted to use this Taylor polynomial to estimate e to the 0.1. Well, we would just plug in a value of 0.1, right? Because again, this is our Taylor polynomial centered at 0. So this is our what e to the x is approximately equal to. Or if you want, it's our linearization. Well, it's not, it's not a linearization, right? Linearization would stop right there. So actually, good point. If we were just asked to do the linearization, our linearization would just be the first two terms here. And if we were using a linearization to estimate e to the 0.1, we would get that e to the 0.1 is approximately L of 0.1, which would be 1 plus 0.1, which is 1.1. But here we're using a better approximation, and we're going to get that our Taylor polynomial approximation, so is going to be for e to the 0.1 is approximately our Taylor polynomial at 0.1. I do really like to point out that you're just replacing the x with whatever value you're trying to plug in. That's why I'm writing more than I probably really need to here. That's going to be 1 plus 0.1. Okay, let's be smart about this. I don't want to write out 0.1 squared. 0.1 squared is 0.01 over 2. 0.1 cubed is 0.001 over 6. And then 0.1 to the fourth is 0.0001 over 24. And I forgot about those divisions there, so that's fine. We'll do it. Because I do kind of want to see how close we are. So 1 plus 0.1 plus 0.01 divided by 2 is 0.05 plus 0.001 divided by 6 plus 0.0001 divided by 24. We get about 1.105170833 compared with the actual value e to the 0.1, which is on the calculator. Wow, we're very close. It's approximately 1.105170918. So we're good to the first what? 1, 2, 3, 4, 5, 6 decimal places. Not too shabby. I mean, not too shabby, except for the fact that we had to use a calculator to get our approximation in the first place. But you could have done it without a calculator; it just would have been horrific. So, yeah. Horrific's probably an exaggeration, but not that much of an exaggeration. Okay, so yes, let's get back around to talking about graphing stuff. And I think we should probably begin to talk about L'Hopital's rule today as well, because it's so you all in Danelle's class have a test on Monday, right? And on that exam is going to be everything up until through chapter 4. I don't actually know this. That was a question. What is your exam going to cover? Up until what chapter? 4.4? That seems likely to me. Do you speak with confidence, or are you just guessing? Okay, it's on the schedule. All right. So it seems very likely that it'll be up through 4.4. Potentially, you might not include 4.4. Like maybe you'll be like optimization, we're just not there yet. I doubt it. But certainly that means 4.3, which is L'Hopital's rule, is probably going to end up on there. So let's do a couple more graphing examples, and then we will talk about L'Hopital's rule. Which is actually, as far as things go, L'Hopital's rule is not that bad. So let's see, I had a few examples here. Do I want to do this one? Yeah, let's do this one. Let's say we want to graph f of x equal to x minus 3 times x to the 2/3 power. Which I feel like we might have found the critical values for before, but we'll find them again. Sorry, you can't see that. So we're going to graph this. Finding all the things. So when I say all the things, I mean we're going to find the intercepts, the asymptotes, the first derivative stuff, meaning relative extrema, and the second derivative stuff, meaning concavity and inflection points. So I guess we can start by finding the intercepts, although I find it kind of it's not the most exciting part here. So the y-intercept Just going to plug in 0 for x. You're going to get f of 0, which is 0 minus 0, which is 0. X-intercepts. You're going to set the whole thing equal to 0. And just speaking generally here, when you're finding the y stuff, it is usually nice to have kind of the unfactored form. By y stuff, I mean like the y-intercept, the horizontal asymptotes if you have any, and any y coordinates of your critical points, whether they're extremo or inflection points. So it's usually nicer to have an unfactored form when you're doing that. Whereas on the other hand, the x stuff, meaning x-intercepts, vertical asymptotes, critical points, the x coordinate, it's nicer to have a factored form of the thing you're working with. So it's usually nice to kind of look at it in two different ways. So for this, I am going to factor out an x to the 2/3 and be left with an x to the 1/3 minus, is that a 3? I feel like that was supposed to be a 2. Let me check my notes here real quick. I feel like, nope, yep, that's supposed to be 3. Okay, why? Okay, I see what's going on here. All right, that's fine. Yeah. Cool, that is a 3. So setting both of those factors equal to 0, we're either going to get x equal to 0 or x to the 1/3 equal to 3, but that's the same as x equal to 3 cubed. So there's my two x-intercepts. Great. Let's find the first derivative stuff. Oh, I should point out, we don't have any asymptotes here, right? This function, I mean, it's not a polynomial, but if you look at like this here, as you go, if x gets really, really big, the whole thing's gonna get very big. If x gets really negatively big, this part's gonna be positive, this part's gonna be very negative, and a positive times negative is very negative. So we're expecting the graph to kind of go up to the right and down to the left. But we probably don't actually have to really think about that because your first derivative stuff will usually tell you that anyway. But we don't have any horizontal or vertical asymptotes here. So let's look at the first derivative stuff. We're taking the derivative. I'm going to look at the unfactored form to take the derivative. I'm going to get 1 minus 3 times 2/3 times x to the negative 1/3. I'm going to simplify this a bit. I'm going to have 1 minus 2 times x to the negative 1/3, or if you like, divided by x to the positive 1/3. And here, you can either think of factoring that out or getting a common denominator. Let's get a common denominator. Let's say we have x to the 1/3 over x to the 1/3 minus 2 over x to the 1/3, or x to the 1/3 minus 2 all over x to the 1/3. So either we have a critical point by setting the numerator equal to 0, which is going to end up giving us x equal to 8. Because the cube root of 8 is 2, and 2 minus 2 is 0. Or we're going to set the denominator equal to 0 and end up getting x equal to 0, which is also a true critical value because it is in the domain of the original function. So 8 makes the derivative equal to 0. 0 makes the derivative undefined. But since both 0 and 8 are in the domain of the original function, they are both real critical values and they should be considered. Even if 0 wasn't a real critical value, we would still put it on our first derivative number line to see what's happening. So first derivative number line. Oh, this is where someone had asked me about like how Dedel does the, oh my gosh, the first derivative test. I'll write it the way I'm going to write it, and then I'll also write it the way he writes it. It's really the same thing. So here's how I would write it. I would put my critical numbers on my number line. And then I'm always thinking about what the derivative is doing. So over here to the right of 8, well, I'm going to look back at my factored version as much as possible. So pick a number bigger than 8, like 27. Why 27? Because it's easy to take the cube root of. The cube root of 27 is 3. 3 minus 2 is positive. The cube root of 27 is positive. Positive divided by positive is positive. And then between 0 and 8, let's pick 1. 1 minus 2 is negative. 1 is positive. So the whole thing is negative. And over here to the left of 0, negative 1. Negative 1 to the 1/3 is negative 1. Minus 2 is still negative. Negative 1 to the 1/3 is negative. And the negative divided by negative is positive. So that tells me that my original function is increasing, decreasing, increasing. Which then tells me that I must have a relative maximum at x equal to 0. We already know the y value there is also 0.
We have a relative minimum at x equal to 8. And we would find the y value by plugging in 8 to the original function. So the y value here would be f of 8, which is going to be 8 minus 3 times 8 to the 2/3. 8 to the 2/3 is 4. 8 minus 3 times 4 is 8 minus 12, which is -4. Just as a contrast, he does this. I mean, the what he's doing for the first derivative test is virtually the same. It just looks a little bit different. He's writing it like this. He's giving himself like more of a table kind of deal and saying over here is x, and then you have the derivative, and then you have the behavior of the function. And he likes to put infinities on there. So over here, negative infinity, and then over here, infinity. And then in between there, we should have all of our critical values. So 0 and 8. I do not love this at all, but that's fine. So then bigger than 8, we saw that the derivative was positive. And then between 0 and 8, the derivative was negative. And between -8, between 0 to the left of 0, it was positive again. I feel like I would put like, I don't know, I would put things between these. It just feels wrong to me to not have those there. And then we know that if the derivative is positive, the function is increasing. If the derivative is negative, the function is decreasing, increasing. It's pretty much the same thing. I think if you wrote it how I wrote it over here, that would be perfectly acceptable. There's nothing wrong with what I've done over here. But that's what I saw him do in the lecture one day. So that's just to see it's the same work. I should also mention, just because some people do ask, they might actually ask you to write the interval where it is increasing or decreasing. That's not terrible. We say it's increasing on the interval from negative infinity up to 0, union 8 to infinity. It's decreasing on the interval from 0 to 8. We do not typically include the endpoints when we say it's increasing or decreasing somewhere. They're always open parentheses, not closed brackets. Okay, let's find all the second derivative stuff, which should be fine. So again, I'll rewrite our first derivative. It was 1 minus 2 over, you guys can't see what I'm pointing to. It was 1 minus 2 over x to the 1/3, or I'm going to write it as 1 minus 2x to the negative 1/3. So then taking the derivative is going to be easy. It's going to be f double prime of x equal to positive 2/3 x to the negative 4/3. So then we're going to figure out where that's either equal to 0 or undefined. I do think it's nicer to write it as 2 over 3 times x to the positive 4/3 to see that it's never going to equal 0, but it will be undefined. So is undefined when x is 0. Okay. So let's look at the concavity. Because that's what the second derivative is really all about. It's about seeing where the function is concave up or concave down. So the concavity is going to change at 0. So f double prime. Let's see, pick a number bigger than 0, like 1. Well, I don't even need to pick anything here, because we know that x to the 4/3 power, that being specifically raised to the 4th, is going to make it positive, whatever you put in, and then after that, it's going to stay positive. Right? Whether you put a negative number to the 4th power is positive, and the keyword that's still positive. A positive number to the 4th power is certainly going to be positive, and the keyword of that is still positive. So basically, if you're raised to a fractional power and the numerator part is an even number, you're done. It's always positive. That'd be true if it was x to the 2/3, x to the 8/3, x to the 1,000,000,000, right? Like any even number over either even or odd, although dividing by evens is a whole other bag of worms. So positive, positive, concave up, concave up. Great, we have all the information we could possibly want. Now we have to try and graph it. So on our graph, we have some important points. We have, let's see, let's go back and look at our list of things. We have the y-intercept at 0, 0. We have the x-intercept at 0 and at 27. Let's not get too wild here. Let's say 27 is like about right there. Again, your scales do not need to make any sense, in my opinion. My what else have we got here? X-intercepts, great. I have my first derivative, so I have a critical point. I have a minimum at 8 comma -4. So that's 27. So let's say 8's about like there. So maybe my minimum's like right about there. Let's say that's 8 -4. Okay, so here's what we've got. We've got that. Let's kind of pull this over here. We've got that our function is increasing up to there, decreasing down to there, increasing afterwards, but it's also always concave up. So concave up, so let's draw this part first here. So from here to here, right, minimum, just keep going up like this. And I think I've learned over the years that it's easiest to think of concave up as anywhere you draw a tangent line for a concave up portion, the tangent line should be below the curve. You could also think of it literally like opening upwards. We say concave up like a cup, concave down like a frown. But it's not always super like cuppy or frowny. Sometimes it's just like a very kind of gradual concave up or down. On the other side here, it should be going this way, right? Because right over there it was increasing, but it should still be concave up. So I shouldn't draw it like that. In fact, so just to go over here, right? I should not draw it like that, right? That would be concave down. I wanted to draw it more like that, where it's concave up, but still increasing from left to right. So it's going to look kind of like, I don't know, like this. And it is a very pointy point there at the origin, because although I do have a relative maximum there, we know that the derivative at that point is undefined. So it shouldn't look smooth. It should look pointy. And there we've met all the criteria of what our points told us we should get. I guess I should label this, right? That's going to be 27, 0. That's kind of all we got. Times, yeah. We'll try to get more graphing in as we progress, but we should probably start talking about L'Hopital's rule because it's not going to go away. We can't just ignore it and pretend like it's not going to happen. All right, I've got papers all over the place here. Yes, there we go. Question.
I just want to ask, when you think the second or first derivative is something they're like very complicated polynomials.
That's true. Do you have an example in mind or?
No, it's just on the home.
Sure. Yeah, so it really kind of depends. Especially if it's like a rational function, I would say, like where you're using the quotient rule for the second time, the numerator can be kind of especially not very nice. It's certainly fine to use a graphing calculator. So I would say, yeah, I would probably use a graphing utility to kind of see where those intercepts might be or those critical points might be. Because sometimes they're nice and sometimes they're not. And if they're nice, you can kind of be like, okay, well then I'm going to factor it in the way I was supposed to. But yeah, there's not a great answer to your question. It's like, yes, sometimes you're going to have polynomials that are a third degree polynomial, and factoring it can kind of be a little bit of a pain. Yeah, I don't have a great answer to your question other than use the tools available to you. All right, let's go ahead and look over here. So the nice thing about L'Hopital's rule is you're not really having to learn any new methods of doing things, right? You're just taking skills you already have and applying them in a new direction. So L'Hopital's rule says the following. If the limit, it is about limits. It's all about, L'Hopital's rule is only about limits. It's not about doing anything else. It's about how we evaluate a limit. So if the limit as x approaches a of f of x over g of x ends up equaling, when you plug in a 0 over 0 or some sort of infinity over some sort of infinity. And when I say some sort of, I really mean it could be a positive infinity over a positive infinity, or a positive infinity over a negative infinity, or a negative infinity over a positive. It doesn't matter what type of infinity you have on the top or the bottom. Anything goes with infinities, as long as it's one sort of infinity on top and any other sort of infinity on the bottom. So if you have something like that, then we can say that the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of the derivative of f of x over the derivative of g of x. That's the whole deal. So if you have a indeterminate limit form, 0 over 0 or infinity over infinity, you can evaluate that limit by taking the derivative of the top and the derivative of the bottom and taking the limit of that. I want to point out we are not using the quotient rule here, right? You're not taking the derivative of the fraction. You're taking the derivative of the top part of the fraction, and then the derivative of the bottom part of the fraction, and then taking the limit of that whole thing. Let's do a couple of examples we already know the answers to. For example, the limit as x goes to infinity of 2x squared plus 1 over 3x squared minus 6x. We already know that the answer to this limit is going to be how much? 2/3, right? Because it's the limit to infinity where the degree on top and the degree on the bottom are the same, and the limit is the quotient of the leading coefficients. But you could also use L'Hopital's rule here. If you plug in infinity, you get infinity on the top, you get infinity on the bottom. And so using L'Hopital's rule, and when we use L'Hopital's rule, it's often a good practice to write L'H over the equals sign so that people know you're using L'Hopital's rule. That's going to be the limit as x goes to infinity of the derivative of the top, which is 4x, and the derivative of the bottom, which is 6x minus 6. Technically, this is still an infinity over infinity type. You plugged in infinity for x, you would get infinity on the top and infinity on the bottom. So we do it one more time. We use L'Hopital's rule again. We do need to write the limit because we're still taking a limit. As x approaches infinity. The derivative of 4x is 4. The derivative of 6x minus 6 is 6. And then the limit of a constant is just the constant, which is going to equal 4/6, which reduces to 2/3. So there's the answer that we already knew we were going to get. Just to show you that L'Hopital's rule does in fact work as we expect it to. Question? So this says, yeah, sorry. This says the limit as x approaches a of f of x over g of x equals the limit as x approaches a of f prime of x over g prime of x. Okay, we're approaching the same thing, it's just now it's of the derivative of f over the derivative of g instead of f over g. Let's look at one other example we also know. The limit as x approaches 0 of sine x over x. We have learned a lot that that limit is equal to 1. But now we can use, but if you plug in x equal to 0, you get sine of 0 over 0, which is 0 over 0, which is an indeterminate form. So another way we can now deal with this limit is by using L'Hopital's rule and saying, hey, that's the limit as x approaches 0. I should use an L'H here. Of the derivative of sine of x, which is cosine of x, over the derivative of x, which is 1. And then we can plug in 0 and get cosine of 0 over 1, which is just 1 over 1, which is 1. Which is what we expected to get, right? We knew that the limit as x goes to 0 sine x over x was equal to 1. But now here's another thing showing us that it is that value. And you could even use it for more complicated ones, like the limit as x approaches 0 of sine of 3x over 5x. Before, I would have said, let's use the wish method, where we rewrite it as sine of 3x over a blank and a blank over 5x, and then put 3x's in both spots and cancel some stuff, and then we get something times 1 times 3/5. But now we don't have to do all that. We can say instead, oh yeah, let's just use L'Hopital's rule and say it's going to be the limit as x approaches 0 of the derivative of the top, and the derivative of sine of 3x is going to be cosine of 3x times 3. On the bottom, the derivative of 5x is 5. And now we can plug in 0 for all the x's and get cosine of 0 times 3 over 5. But that's just 1 times 3 over 5, which is 3/5. Which is exactly what we would have gotten if we had done it the other way. So that's great. L'Hopital's rule definitely works for limits that we've already done before that are 0 over 0 or infinity over infinity types. Only those, right? You can only use L'Hopital's rule for those types of limits. Any other limit, you either can't or you have to rewrite it first. Sometimes you just can't. So just actually, that's a good point here. If I was to ask, yeah, what's the limit as x approaches 0 from the right of the natural log of x divided by x? This is not a case where we can use L'Hopital's rule, because if you think about what's happening here, the denominator is getting very, very close to 0. And natural log of x, as x approaches 0 from the right, what is the natural log function doing? This is where it's really good to have a graph of it in your mind. The natural log of x is doing, it's doing this. You have a vertical asymptote there. So as the x gets closer and closer and closer to 0, the natural log of x goes towards negative infinity. So just ask yourself this question. If you have a really giant negative number divided by a really small positive number, the overall sign is negative, and the overall value is tiny or giant? Giant, right? Giant number divided by extra small number is even more giant. So this is going to be a negatively giant number. No need or actually no ability to use L'Hopital's rule here. If you use L'Hopital's rule, I think the answer was going to come out wrong. Right? In fact, let me just show you. If we were to incorrectly apply L'Hopital's rule, right? Because again, it's not a 0 over 0 or infinity over infinity. You'd have the limit as x approaches 0. The derivative of the top is 1 over x. The derivative of the bottom is 1. And now, as x goes to 0 from the right, 1 over x goes to positive infinity, which would not be the correct answer to this question. So I just want to emphasize here, you can only use L'Hopital's rule when you have the right type of indeterminate form. 0 divided by 0, or some sort of infinity divided by some sort of infinity. But the reason we're really talking about this is because there are plenty of limits that we can't evaluate using the methods we've learned already. So for example, we would like to be able to find the limit as x approaches infinity of x squared divided by e to the x. And if you just plug in infinity, infinity squared is infinity, and e to the infinity is also infinity. What to do? L'Hopital's rule. Often when we write this, we put this like in quotes because it's not like really a number. So we're like, yeah, if you were to do that, that's the kind of thing you would get. But so now we're going to use L'Hopital's rule. So we're just going to rewrite it. Still going to write the limit as x approaches infinity. But now we're going to take the derivative of the top, which is 2x, and the derivative of the bottom, which is e to the x. And we still have infinity over infinity. Right? The top is still getting infinitely large. The denominator is still getting infinitely large. So we do it again. Often you'll have to apply L'Hopital's rule like 2 or 3 times before you get to a place where you can actually do it. So I should back up a little bit here. Whenever I'm trying to evaluate the limit and I know I'm using L'Hopital's rule, every time directly after I've applied L'Hopital's rule, then I think about plugging in whatever x is approaching. And if I get a number, 0 or 5, 23 or negative 17, I stop. That's my answer. But if I don't, if I get some sort of still infinity over infinity or 0 over 0, then I have to use it again. So I'm going to use L'Hopital's rule again and get the limit as x approaches infinity of the derivative of 2x is 2. The derivative of e to the x is still e to the x. And now the numerator isn't going to infinity. It's going to 2. And the denominator is getting infinitely large. And if you have something that's finite divided by something that's infinite, that's going to end up being 0. I will point out, oh, question? When you say constantly be 0 for 0.
No matter how many times you take the derivative of it.
Yes, there are examples. So I would say, here's my answer to your question. There are examples of limits where using L'Hopital's rule gets you in an endless loop, where you can never get to an answer that way. Let me say one thing about this, and then I'll also do an example like that. So I just want to point out that it wouldn't have mattered if we'd had x squared or x to the 200th power.
the e to the x derivative is always going to be e to the x. Whereas the derivative of any polynomial, if you do it enough times, eventually gets down to a constant term. So you could say similarly that if you're taking the limit and say x goes to infinity of x to the 200th power over e to the x, with enough applications, you would eventually get to the limit as x goes to infinity of some constant still divided by e to the x, which would then be 0. The constant would be 200 factorial, in case you're curious. Like it'd be 200 times 199 times 198 times 197, all the way down to 2 times 1. Yep. So, or as I would say, e to the x, an exponential function, is always going to dominate any polynomial function. So e to the x wins. It gets bigger faster. So if this was flipped over, if it was e to the x over x squared, that limit would end up being infinite because eventually your numerator would grow infinitely large, your denominator would be a constant. To answer your question, which is a very good question, so I can remember the example I'm thinking of, I believe it's something like the limit as x goes to infinity of, let's see, I believe the one I want is the square root of x squared plus, it doesn't really matter, over x. So, and this actually brings up a really good point, is L'Hopital's rule is a great tool, but it doesn't work for everything. And sometimes it's actually too, like, it's kind of, what's the saying, like using a, I don't know, like an atom bomb to kill an ant, I think is the saying, right? Sometimes you don't need to use the biggest tool in your toolbox. Sometimes the smaller tool is a great tool to use. I've got another example of that after this one. So, yeah, that's fine. So if we try using L'Hopital's rule, and I'll point out we can use L'Hopital's rule here because it is an infinity over infinity type of limit, right? The top's going to infinity, the bottom's going to infinity. So if we use L'Hopital's rule, look what happens. You get the limit as x goes to infinity. The derivative of the bottom is 1. The derivative of x squared plus 1 to the 1/2 power is 1/2 times x squared plus 1 to the negative 1/2 times the derivative of x squared plus 1, which is 2x. And now we definitely, and this is something to take heart, we definitely want to simplify this expression before we try doing anything else. I mean, I guess, no, I don't even want to plug in infinity yet. I'm going to simplify. The 2's cancel. And the x stays on top, and the x squared plus 1 to the negative 1/2, I'm going to put down to the bottom as x squared plus 1 to the positive 1/2, or x squared, or the square root of x squared plus 1. And notably, all that I've accomplished is I've essentially switched the places of x and the square root of x squared plus 1. And if we do it again, they're just going to switch right back. So if we do this one more time, just so you can see it. Oh, don't forget the limit. The derivative of the top is just 1, and the derivative of x squared plus 1 to the 1/2 is 1/2 times x squared plus 1 to the negative 1/2 times 2x. And if we simplify this, the x squared plus 1 to the negative 1/2 comes up to the top, and you get the limit as x goes to infinity of, on top, x squared plus 1 to the negative 1/2, sorry, positive 1/2, on the bottom, just x. And look, we've done a bunch of work and ended up right where we started. How disappointing. So there are some limits that even though L'Hopital's rule applies to them, it gets you nowhere. So then the question becomes, well, how do you deal with a limit like this? There are other methods. In this case, I will actually point out, if you have a limit where you keep getting basically you keep flipping back and forth over, it's probably going to be 1, because whether you're taking the limit of this or the limit of 1 over it, it's going to be the same value. And so if something is equal to its own reciprocal, there's only two real numbers that are equal to their own reciprocals. One of them's 1. 1 over 1 is 1. What's the other one? Negative 1. 1 over negative 1 is also negative 1. Those are the only two numbers that are equal to their own reciprocal. So if you have a limit that's exhibiting this behavior, it's probably going to end up equaling either positive 1 or negative 1. Let's check it out. So we do this here. So here's the way you actually deal with a limit like this. Limit as x goes to infinity of the square root of x squared plus 1 over x. You take the inside of the square root and you factor out an x squared. I'm gonna have x squared times 1 plus 1 over x squared. So then we get the limit as x goes to infinity. Oh, I should have done negative infinity. That'd be much more exciting. We're going to break it up as the square root of x squared times the square root of 1 plus 1 over x squared, all over x. Now be careful. The square root of x squared is not just x. It's the absolute value of x. In this case, since x is already positive, we're safe. It's just going to be x. But if we were doing the limit as x goes to negative infinity, then this absolute value of x, if you can come in, would be negative x. It's right there, Maria. Oh. So here we can say that the limit as x goes to infinity of just x times the square root of 1 plus 1 over x squared, all over x. And then those x's do cancel. And then you get 1 plus 1 over infinity, which is just 1. And the square root of 1 is 1. So yeah, really good question. Sometimes L'Hopital's rule won't get you anywhere. Or, to kind of go along with that theme for one more example, sometimes it's just too terrible to use. Here's another example of where, although we could, actually not another, here is an example of where we could use L'Hopital's rule, but you really are going to regret it. The limit as x goes to 0 of sine cubed of 2x over x cubed. I kind of don't even want to try doing using L'Hopital's rule because it's really, really awful. Let me show you the first step. Let me point out that it is allowed for us to use L'Hopital's rule. So if we plugged in 0, we get sine of 0, which is 0, divided by 0, which is 0. So check it out. This is, I'll point out that sine cubed of 2x is sine of 2x quantity cubed. So when we take the derivative of the top, we're going to get 3 times sine of 2x quantity squared times cosine of 2x times 2, all over 3x squared. We can make our lives a little bit less terrible, cancel a 3 there and a 3 there, and rewrite this as the limit as x goes to 0 of 2 times sine of 2x squared times cosine of 2x, all over x squared. But then in this next step is where things start to get really terrible. Because to take the derivative of the top in this next step, I should point out, I still need to use L'Hopital's rule because if I plugged in 0, on top I would get 2 times 0 times 1. On the bottom I would get 0. That's 0 over 0. It's still an indeterminate form. So we shouldn't do another step here because the next step is terrible. Look what happens. You have to use the product rule and the chain rule. You're going to end up getting something like, I don't know, the bottom is going to be 2x. The top is going to be 2 times, oh my goodness, the derivative of that, 2 times sine of 2x times cosine of 2x times 2 times the other cosine of 2x that was just hanging out, plus, then you switch it up, you get sine of 2x squared times the derivative of cosine of 2x, which is a negative sine of 2x times another 2. Ugh. And then it's still a 0 over 0. So you have to do L'Hopital's rule one more time, which we're not going to do because it's terrible. So here's what you should do here. Don't do this. Instead, use the fact that we know things about sine of 2x over x. We can rewrite this as the limit as x goes to 0 of sine of 2x times sine of 2x times sine of 2x times something over x cubed, and then just fill it in the nice way we did way back when. I want a 2x down here. I'm going to put a 2x up here. I want a 2x down here. I'm going to put a 2x up here. I want a 2x down here. I'll put a 2x up here. So then this ends up equaling 1 times 1 times 1 times 8, which is 8. So sometimes, even though L'Hopital's rule is a perfectly fine rule to use, it's not going to be the easiest way to do a problem. That said, it's a great tool and you should definitely get comfortable using it, but there's just some times where it's not the best. Let's see. Yeah, sure. That's fine. That. There was another example I had here. 1 second. Grab this other example I had. What about the following? Limit as x approaches 2 of x cubed minus 5x plus 2 over x squared minus 4. As with any limit, we should start by just trying to plug it in. If I plug in 2, I'm going to get 8 minus 7 plus 2, which is 0, over 4 minus 4, which is 0. We could do this by just factoring. Although factoring the top might be a little bit of work. It's probably easier just to use L'Hopital's rule here. So if we try using L'Hopital's rule, we're going to get the limit as x approaches 2. The derivative of the top is 3x squared minus 5. The derivative of the bottom is 2x. If we plug in 2, we're going to get 3 times 2 squared minus 5 over 2 times 2, which is 12 minus 5, which is 7, all over 4. Seems... No, I guess that's fine. Yeah, that seems fine. Yeah. Or you could have factored the top and canceled x minus 2. But I think this is fine. Well, let's look at some other things. So some things that might not look like L'Hopital's rules questions to start off with. For example, the limit as x approaches 0 from the right of x times the natural log of x. Definitely not L'Hopital's rule to start off with because it's not a fraction. So I would say the first thing you should think about if you have a limit and you're considering L'Hopital's rule is, do I have a fraction? If the answer is no, then you cannot use L'Hopital's rule yet. We don't have a fraction, so we can't use L'Hopital's rule yet. We should probably try plugging it in. I would say I would encourage all of you to get super comfortable with the fact that as x approaches 0 from the right, the natural log of x goes towards negative infinity, right? We've got that vertical asymptote. So we can see here that we have a very, very small number times a very, very large negative number. And I want to emphasize strongly here that that is not 0. That is a small positive number that's close to 0. Because if you think of it as being 0, you could kind of try to justify to yourself that 0 times anything is 0. But that's not what we have here, really. We have a very, very small number times a really, really negatively big number, which could end up being anything, depending on how small versus how big. This is another type of indeterminate form, where you have a small thing times a big thing, which we call a 0 times infinity. So in this case, we're going to rewrite it so that we have a fraction. So here's how we're going to rewrite it. We're going to rewrite it as the limit as x approaches 0. We typically try to leave the more complicated thing on top. So I'm going to leave the natural log of x on top. And then I'm going to bring the x down to the bottom as its reciprocal. So I'm going to rewrite this as natural log of x divided by 1 over x. Which now should be the right kind of form because look, if you bring the thing that's going to 0 down to the bottom, that's like having a negative infinity divided by 1 over 0. But a 1 over 0 is like a positive infinity in this case. So this is exactly like a negative infinity over an infinity, which is exactly what we have over here. So whenever you take a 0 times infinity and bring one of the things down to the bottom as its reciprocal, it's kind of reciprocaling its nature. A small thing becomes a big thing becomes a small thing. So the 0 coming down to the bottom becomes something that's getting large. And now we can totally use L'Hopital's rule. We're going to have the limit as x goes to infinity. Sorry, as x goes to 0 from the right, apologies, of the derivative of the natural log of x, which is 1 over x, and the derivative of 1 over x, which I'm thinking of as x to the negative 1, whose derivative is negative 1 times x to the negative 2, or negative 1 over x squared. Now be careful here. It's easy to convince yourself that we should keep using L'Hopital's rule if we're not careful. If you plugged in 0 from the right now, you'd have a 1 over 0, which is like positive infinity, and a negative 1 over 0, which is like a negative infinity. You could be like, oh yeah, I have an infinity over infinity type. I could still use L'Hopital's rule. Technically, you could, but we should simplify before we try to keep going forward. So if I simplify this, I'm going to write this as the limit as x approaches 0 of 1 over x times the reciprocal of negative 1 over x squared, which is x squared over negative 1. I can cancel an x. I'm left with the limit as x approaches 0 from the right of essentially just negative x. If I plug in 0 now, I'm totally going to get just 0. So in this case, the 0 kind of won out. This thing was getting smaller much, much faster than it was getting larger, which makes sense if you think about the graph of the natural log of x. It gets large, but very, very slowly, whereas x approaching 0 does it relatively quickly. Do we have time? Yeah, we have time. I do want to show you one more example because I think it's really cool, and also because it's not just because it's cool, because it's also worthwhile. So here's a limit we were talking about relatively recently. The limit as x goes to infinity of 1 plus 1 over x to the x power. And everyone should be able to tell me that that limit's going to be equal to what really famous number? E. But now we're going to see it using L'Hopital's rule. So I'll point out that if you plugged in infinity right now, you'd have 1 plus 0 essentially to the infinity power. So this is called a 1 to the infinity indeterminate form. But again, I want to remind you, it's not really 1. It's a number that's very, very close to 1. And it's being raised to a very, very large power. So you essentially have like 1.00001 times itself a bunch of times. And it's going to get back up being close to E. So here's how we're going to actually deal with this. We're going to look at, yeah, we'll do it that way. We're going to look at the limit as x goes to infinity of the natural log of 1 plus x to the x power. So I want to point out we've changed our value, right? So what I'm really actually saying here is that 1 plus 1 over x to the x is equal to e to the natural log of 1 plus 1 over x to the x. And then we're going to ask ourselves what this is equal to. And then our actual answer is going to be e to whatever we get there. All right, let's do it. By the way, the reason we're doing this is because the only way we can really get a variable out of the exponent is by taking the natural log of that expression. So we're going to get, and I'll do this quickly because it's 1149. The limit as x goes to infinity of x times the natural log of 1 plus 1 over x. But now we have an infinity times a 0 type because x is going to infinity, and the natural log of 1 plus 0 is the natural log of 1, which is 0. So this is an infinity times 0 type. So then we're going to bring the less complicated thing down to the bottom. So we're going to write this as the natural log of 1 plus 1 over x divided by the reciprocal of x, which is 1 over x. And now it's a 0 over 0 type. So now we can use L'Hopital's rule. The derivative of 1 over x, just like before, is negative 1 over x squared. The derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff, and the derivative of 1 plus 1 over x is 0 plus negative 1 over x squared. Again, hey, look at that. Those negative 1 over x squared are going to cancel out. How convenient is that? So we're left with the limit as x goes to infinity of 1 over 1 plus 1 over x. And now the 1 over x is going to go to 0, and we're going to be left with 1 over 1. So since the limit of this part is equal to 1, the limit of this part is going to be e to the 1. So we can say that the limit as x goes to infinity of just 1 plus 1 over x to the x is equal to e to the power of the 1 coming in right there, which is just e. So there's some more proof of this thing we've been saying is true for a while, that as x goes to infinity, 1 plus 1 over x to the x power does in fact get closer and closer to the number e. Which is cool. All right, it's 11:51. I should stop talking.